I now call to order the Society's 2480th meeting in what is now the 152nd year since its founding on March 13, 1871. Good evening, everyone.
Good evening, Larry.
My name, as many of you seem to know, is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium at the Cosmos Club, and everyone on YouTube tuning in to the live stream of tonight's PSW lecture by Tabitha Dodson on nuclear rocket propulsion. The Society is grateful to PSW full year series sponsors, PSW member Mike Hilton and Hilton Associates, and the Policy Studies Organization in cooperation with the American Public University. We are also grateful to PSW member Tim Thomas for his generous support of the fall lecture series. Thank you, Tim. And we are additionally grateful to the sponsors of tonight's lectures, Anik Associates and PSW member Anik Innig, who is also here. Thank you, Eric. Tonight is the Society's annual meeting and the annual report on the status of the Society. First, the report of the Audit Committee. We would have Lloyd Mitchell, who was on the Audit Committee, give you the report, but he's busy running a camera. So I will do it in his stead. The committee met earlier this week. The finances were audited in detail and found to be sound and without objection. A copy of the Audit Committee report and a financial report are available by request to corresponding secretary Robin Taylor at correspondingsec@pswscience.org, and Robin is the back running the live stream and the recording, so you can ask her in person. A few words on the state of the Society. I'm pleased to report that the Society was able to hold 18 meetings, all of them in person during fiscal year ending June 30th, 2023. Membership was slightly above the previous year. Financial support increased significantly, and the Society was able to end the year in the black despite the tripling of Cosmos Club charges and increases across the board for all other services required to carry out the Society's activities. We are very grateful for all this financial support, especially lecture series and individual lecture sponsorships by our generous supporters. If any of you are interested in sponsoring a lecture or giving large amounts of money, please do see me as soon as possible. The Society posted edited recordings of all meetings to the PSW website and to the PSW Vimeo and YouTube channels. There are now 199 videos in 15 playlists with 850,000 collective views. Newly posted videos were viewed several hundred times to several thousand times in the first 2 weeks after posting, and there are now about 9,500 subscribers to the PSW YouTube channel. The Society is looking forward to continued growth in the coming year, increasing its capacity to utilize projective and participatory technologies like YouTube and Zoom, and to some new programming initiatives. Once again, financial considerations will require focused effort to be sure that dues and donations meet the ever-increasing costs of operations. Sincerely, Larry Milstein, President. I am pleased to announce the following new members: Louis McIntyre, retired engineer and naval aviator and book author interested in physics, who learned the PSW from the PSW YouTube channel. Gerald Price, a software engineer retired from SRA International, particularly interested in cultural dynamics, who is a returning PSW member, having moved to the far reaches of New England and originally learned of PSW from colleagues. Joel Bauman, Dobbs Professor of Chemistry at Emory University, interested in theoretical and computational chemistry, who learned at PSW from the Cosmos Club and the PSW website. Addison Stark, who's with us tonight, CEO of Atmos Zero, interested in physics, engineering, and climate technology, who learned a PSW from other PSW members. Kenneth Sanders, expert consultant on infectious diseases, interested in virology, immunology, quantum mechanics, and cosmology, who learned a PSW from the PSW YouTube channel. And tonight's speaker, Tabitha Dodson, who learned a PSW from the invitation to speak here tonight, and whose interest will be clear in some part from tonight's lecture. We welcome them all to membership. If you are a new member and you have not yet received your signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, aka PSW Science, please see me after the lecture so I can give you a copy. In it you'll learn why PSW was formed, who formed it, what the original bylaws were, and there will be minutes of many of the first meetings of the Society, in which you can appreciate the range of subjects that interested the founders and the members at the turn of the 2 centuries ago. Erica Kane will now present the minutes of the 2479th meeting and the lecture by Bill Merrill and Sam Brody on the Ike Dike project to protect Texas coasts. The minutes being prepared by PSW Recording Secretary Camille Lance, who's unable to be with us tonight.
On June 16th, 2023, from the Powell Auditorium of the Cosmos Club in Washington, D.C., and by Zoom webinar broadcast on the PSW Science YouTube channel, Vice President Robert Thompson called the 2479th meeting of the Society to order at 8 p.m. Eastern Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. Vice President Thompson then introduced the 2 speakers for the evening, William J. Merrill, the Regents Professor, President Emeritus, and the George P. Mitchell Chair of Marine Sciences at Texas A&M University at Galveston, and Samuel D. Brody, the Regents Professor and George P. Mitchell 40 Chair in Sustainable Coasts in the Department of Marine and Coastal Environmental Science at Texas A&M University Galveston campus. Their lecture was titled, "The Ike Dike Project to Protect Texas Coasts." Dr. Merrill began by explaining that the long title for the talk was Protecting America's Coast from Flooding in the Face of Rapid Climate and Land Use Change. The speaker then reviewed expectations on population growth and the implications of population to pollution and potential for human adaptation to a changing climate. The speaker then reviews 2 reasons why adaptation is especially important at the coasts. First, the speaker explains, the U.S. is still building and moving to the coasts, and in the past, increasing coastal storm losses have correlated well with the increasing population and related infrastructure. The second reason regarded coastal vulnerabilities, including infrastructure and threats. Dr. Merrill then argued the next century will be an era of coastal adaptation and reviewed the approach he and Dr. Brody will take to make this argument. Dr. Brody began by thanking President Milstein and the Society for the introduction to speak. Dr. Brody continued by emphasizing that there is an ongoing crisis due to mega events which cost billions of dollars. The speaker emphasized this point by reviewing a map of flood insurance claims. The speaker mentioned the current recovery-based approach to management. The mitigation and preparedness of floods revolves around insurance, an outdated 100-year floodplain model, and a method of chasing the last great storm. As an example, the speaker reviewed an example of coastal storm protection projects implemented at the federal level in the Houston-Galveston region. He began the example by reviewing a map of the physical flood risk and comparing this with estimates of land use and sea level rise. The human-built environment, the speaker argued, is a main driver of flood risk and causes urban flooding. Urban flooding is increased by inadequate draining infrastructure, development that places obstacles to streams, and development that does not recognize natural drainage patterns. The speaker then argued for a protection-based environment to management, such that flood losses are eliminated, as opposed to adapting to the losses. To successfully implement this approach, the solutions need to be regional and implementation local. The speaker calls this the coastal spine strategy, which aims to keep the ocean surge out of Galveston Bay by using a gated coastal barrier. The media, Dr. Brody explained, dubbed this as the Ike Dike. The components of the Ike Dike are the Galveston seawall, land extensions, and floodgates. The speaker then reviewed flood maps before and after the implementation of the Ike Dike to demonstrate its usefulness. Dr. Brody then reviewed a book written by the speakers called Coastal Flood Risk Reduction, which summarizes the previous decade of the research performed. The speaker went on to discuss the policy implications for future flood resistance. He highlighted the need to consider life cycles of projects, cumulative impacts of developments, and protection-based approaches with emphasis on adaptation. The need for better communication of flood risk was also emphasized. Dr. Merrill then reviewed specifics to the policy implication. The speaker argued the scientific challenges have mostly been solved and that the policy difficulties remain a challenge. The speaker reviewed the next steps for the Ike Dike. First, Congress has authorized but not yet appropriated $34.4 billion for the construction of the project after determining it is in the national interest. Additionally, the design must be finalized, operational costs must be allocated, and the project must be completed prior to a destructive event to the region. Next, the question and answer period began. First, a member asked about the implications to the D.C. region, specifically the Chesapeake Bay, Potomac River, and Anacostia. Dr. Merrill answered by reviewing the water levels. The sea level rise in the D.C. region is expected to be 12 inches by 2050. The Chesapeake Bay is already showing signs of increasing water levels, and the Potomac is showing signs of tidal flooding problems. Major rainfall is expected in the region and will cause urban flooding because of the inability of the existing infrastructure to handle the runoff. Another member asked from online whether AI tools have been applied to the data sets used for predictive models. Dr. Brody enthusiastically responded with yes. Machine learning has been used to learn where development will occur in the future, which enables scientists to identify where people will build and what risks will emerge as a result. After the question and answer period, Vice President Thompson thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. Vice President Thompson adjourned the meeting at 9:56 p.m. The temperature in Washington, D.C., 18 degrees Celsius. Weather clear. Attendance in person in the Powell Auditorium, 26. Number of streaming online viewers, 26, for a total in-person attendance of 52. And views during the 2-week period after the lecture, 277. Respectfully submitted, Erica Kane on behalf of the recording secretary.
And thank you, Cameo, who can't be here, for preparing the minutes to be read. The minutes are accepted as read and will be posted to the website in due course. And we now turn to tonight's lecture by Tabitha Dodson on DARPA's DRACO project to develop nuclear propulsion systems for space exploration. Tabitha is the program manager for the demonstration rocket for Agile Cislunar Operations, more easily known as DRACO. Our interests focus on advanced space payloads, rocket propulsion, especially nuclear propulsion, and plasma engineering. Prior to becoming a program manager at DARPA, she was a systems engineering and technical assistance contractor at Griffin Schaefer Government Services within DARPA, where she served as the chief engineer of the DRACO program to build and test a nuclear thermal rocket. Upon becoming a government employee with DARPA, she continued to serve as DRACO's chief engineer and also served as a deputy program manager. Tabitha has also served as adjunct professor of aerospace engineering at the United States Naval Academy and as adjunct professor in the Aeronautics and Astronomics Department of the Air Force Institute of Technology. She earned a BS in physics, sociology, and anthropology, an MS in space policy, and a PhD in mechanical and aerospace engineering at the George Washington University, and in addition, a PhD in applied physics at the Air Force Institute of Technology. Please address her as Dr. Doctor. All questions will be fielded after the lecture during the Q&A session. Tabitha, the stage is now yours.
So Larry tells me that I am allowed to go into technical details and that this is a technical audience, and that's something that I'm normally, I'm not at liberty to do when I'm giving briefings. Normally my briefings go by very quick and to the point, and I'm coached to stay out of the technical weeds. So you guys get to bear with me while I have a few slides that actually get into those details. But nuclear thermal rockets are a very interesting subject matter to actually give a briefing or a lecture for, because they span so many different topics. There's obviously the aerospace rocket element of it. There's nuclear, an entirely different topic normally. There are all kinds of policy and legal topics we can get into, which is a lot of fun for people in DC especially, because that's the livelihood of a lot of people in this city. And so I might just touch on every single one of those things tonight. And I'll not only go into the great technical detail in some things, but also go very high level in some other places. So your brain hopefully won't be too sleepy throughout the entire duration of this presentation. So DRACO is a DARPA program. We have a contract with the prime contractor, who is Lockheed Martin. Lockheed Martin has several subcontractors, with the largest one being BWXT, who's going to be providing the nuclear reactor. BWXT also provides reactors for the United States Navy. The program itself is a roughly 50-50 partnership with NASA. We're both providing roughly 50% of the funds for the contract. Having NASA on as a partner is excellent, given their great rocket engine expertise, and we definitely need that, given that this is, above all else, a rocket engine. You'll see there on our artist depiction of the stage, let's see if this will work. There we go. The Space Force logo on that side. I was giving it a little test drive. The Space Force is providing the rocket that's going to be taking DRACO into space. And as you could imagine, the rocket is not cheap. So we're roughly split a third between our respective agencies when it comes to the investment going into this program. So I want to say just a few words about DARPA as an agency. DARPA, I've always believed that, and obviously still believe it today, is a very unique and important place. And the mission of DARPA came about in response to the launch of Sputnik by the Soviets. And so the DARPA agency was created such that we would never be surprised again in that way. So we will both prevent technological surprise and create our own technological surprise by creating our own Sputnik moments. So putting a nuclear thermal rocket in space makes for a perfect Sputnik moments. And so if you're unfamiliar with what has DARPA done before, one of the things that we like to remind people of is that the internet started with DARPA. So before DARPA, it was known as ARPA. The internet started out as ARPANET. DARPA is also known for lots of different X-planes, prosthetics, all kinds of robots, like the robotic challenges, like the you can look on YouTube of all the cool stuff that robots have done thanks to DARPA. So I think maybe the last thing I'll say about DARPA is the fact that this is a program within the Tactical Technology Office. TTO does a lot of platform system demo type of programs, but there's also other offices within DARPA that do amazing things. Like we have a BTO, which is our Biological Technology Office, and they did some really important things to help out with the COVID pandemic, and really helped with getting those things situated when it comes to the vaccines. So the first thing I want to do in this lecture is I want to set the tone.
Provide the funds which are needed to meet the following national goals. First, I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish. But in a very real sense, it will not be one man going to the moon. We make this judgment affirmatively. It will be an entire nation, for all of us must work to put him there. Secondly, an additional $23 million, together with $7 million already available, will accelerate development of the rover nuclear rocket. This gives promise of someday providing a means for even more exciting and ambitious exploration of space, perhaps beyond the moon, perhaps to the very end of the solar system itself.
So the reason I played that video is because for a few different reasons. A lot of people obviously know that Kennedy had a couple of famous speeches, one Rice University and also one to Congress. Actually, he had multiple famous speeches, but when it comes to his speeches about the moon and Apollo, it's very rare to find a person who knows the whole speech and know that he also talks about nuclear rockets, because as part of the broader plan of the Apollo program, nuclear rockets were meant to be the next upper stage that were to sit on top of the Saturn. And so I wanted to, and I have a slide later that gets into, it was a political decision, not a technical or safety decision, to cancel the NERVA rover program, and so we'll talk about that later in this presentation. But I wanted to put this up front just to show the reality of this technology and also the importance of the technology from the perspective of the United States' ownership over this technology and how important it is for us to get this back on the table and getting it developed in this decade. All right, so the actual lecture itself. So before I get into DRACO, which is roughly half of the lecture that I'm going to be getting into today, I think it behooves me to explain what exactly is a nuclear thermal rocket, get into some technical details into the reactor itself. I could have gotten into more details into the space part of the rocket and the astrodynamics and things of that nature, but when it comes to the general, when it comes to the public writ large, and the thing that I think people need the most education on it is the nuclear side of things. So that's what I'm going to choose to get into a little bit more technical detail on. Touch on the history of nuclear thermal rockets before getting into the actual program itself. And so I'll provide a lot of philosophy into how we're going to conduct our on-orbit demo, our stepwise approach through the experiment, and then end with some thoughts on the future of the program. So the specific impulse of a nuclear thermal rocket is the thing that is really the selling point when it comes to what makes this propulsion system better than the other propulsion systems you have for in-space maneuver. So you can think of the specific impulse or the ISP like the efficiency, the gas mileage at which you use your propellant, just like the gas mileage or the efficiency of what you would have in your car. And you can see by this sort of basic chart here, with respect to specific impulse versus thrust, a nuclear thermal rocket has thrust on the order of an upper stage rocket engine. So an upper stage is the smaller rocket that sits on top of the first stage, and that's the thing that actually takes your payload to where it needs to go. So it'll deliver a payload to GEO or to the moon. But unlike upper stage rocket engines, nuclear thermal rocket engines have high specific impulses on the order of electric thrusters. And so unlike a chemical thruster, which burns for a very short amount of time and then it runs out of gas very quickly because it has that low specific impulse, electric thrusters, you can burn them for months without running out of gas. However, because their thrust is so tiny, it takes months to get anywhere. So with nuclear thermal rocket engines, you can burn for longer and you can get places quickly. So the way that you can achieve the high specific impulse of a nuclear thermal rocket is you can use this approximation equation that ISP is approximately the square root of the chamber temperature divided by the molecular weight of the propellant. And so nuclear thermal rockets are able to achieve both high chamber temperature and use the lowest molecular weight option for propellant, which is hydrogen. So when you're looking at chemical propulsion systems in general, so biprop, monoprop, you always need a fuel and an oxidizer, and so you will not be able to use just hydrogen in that case. So for instance, for a chamber temperature of about 3,000 degrees Kelvin, you will achieve a specific impulse of about 900 seconds ISP, which is about 3 times higher than what you can get with a current chemical rocket engine. So if that's hard to visualize or to understand exactly what am I talking about, I have a couple of little cartoons here to perhaps help visualize that. So for these two rockets, one chemical biprop on the far side of the screen, and a little nuclear thermal rocket on the other side. Both of these tanks are sized for the same performance. So you can think, you know, I'm going to the same place in space, or I'm carrying the same weight of cargo. But obviously one's much bigger than the other. And so for a nuclear thermal rocket, which is on this side of the specific impulse chart. Do you want me to stand here?
No, I want you to use.
Oh, okay, sorry. There we go, okay, thank you. Okay, so it's all the way over here. You can think for 900 second size P, for roughly, you know, between these two curves of performance, you can get a tank that's somewhere shy of 1,000 to 2,000 kilograms of propellant. Whereas if you're looking at a chemical propulsion system with specific impulses, which are typically less than about 375, you're looking in the multiple thousands of kilograms of propellant. And this curve for higher performance is going to move in this direction. And obviously the sizes of the tanks are going to grow in both cases. But for the nuclear thermal rocket, it tends to stay in this sort of vicinity, whereas for chemical, you're quickly approaching the tens of thousands of kilograms, which is fine if you have a rocket like the SLS, which NASA does have. And they can use that to get heavy cargo in the order of tens of thousands of kilograms to places like the moon. However, for the Space Force, which has NSSL type of rockets, we do not have quite the lift capability of an SLS rocket. So for something like what we have now available to the Space Force, which is a SpaceX rocket, ULA rockets, we don't need something the size of an SLS to take our upper stages to the volume between the Earth and the Moon. So there's a cutoff point here on this axis where the first stage just cannot lift your second stage. It's just too heavy to get it into space. So even if you had a second stage rocket, which was 100,000 kilograms of propellant, you could never get it off the Earth, or at least not with the rockets that we have now. So again, you want to have your second stage rocket be as tiny as possible, or at least the tank of propellant, such that you can have more cargo available and have smaller first stage rockets to get you there. So here's the part that I promised. And before I get into the actual weeds with respect to the nuclear physics and engineering, we need to go over some vocabulary words, because I'm going to be saying these words here and there, and it's important that you know what they mean, so as not to confuse them with other things. So firstly, Halu, high assay low enriched uranium. This is the kind of uranium that DRACO is going to be using. Halu is very popular in the nuclear community. There's a bit of a nuclear renaissance going on across all of nuclear reactor companies, terrestrial-based and also space-based, and they're all very interested in Halu. And that is also policy-driven from the nuclear proliferation crowd, who would like to see less highly enriched uranium, which is weapons grade, and more Halu. So 19.75 enriched, enriched U-235, uranium-235. That's the thing that you, that's the radioisotope that you need to actually generate the fission. Sits kind of in the middle here between low enriched uranium, which is what you're used to seeing for commercial power reactors, and highly enriched uranium, which is both weapons grade, naval reactors uses it, and also the past NERVA rover program used weapons grade, highly enriched uranium. So the next word I have here is fuel. So for the people in the rocket community, they're used to using the word fuel to mean the propellant, like the hydrogen, or the thing that you mix with the oxidizer. For a nuclear thermal rocket engine, we don't use that word to mean our hydrogen. We use it to mean our nuclear fuel. Also because we don't have an oxidizer, so we don't have to say this is our fuel, this is our oxidizer. So this is an example of a fuel. This substrate here, that white stuff is tungsten. UO2 as seen here in the little black Dalmatian sort of spots. This particular fuel happened to have cracked during some kind of test. But this is an example of a kind of fuel that you could have in a nuclear thermal rocket engine. This was back when they were looking at using tungsten as a kind of a fuel back in the day. But that is what I mean when I say fuel, uranium plus some sort of matrix that supports it. Next word here, moderator. And I have at least a couple of slides dedicated to moderators. So moderators are extremely important, especially when you're talking about Halu or low enriched uranium, because they do everything they can to slow down neutrons and control the energy spectrum of the neutrons in order to make sure you have some good fission. Hydrogen, graphite make great moderators, and again, I'll get into it later a little bit more. Critical, or criticality, is one of our favorite words to use, but it's just another way of saying the reactor's on. Yeah, I've made the reactor go critical, I've turned it on. If it's KEffective less than 1, the reactor is subcritical, and I have another slide dedicated to what exactly is KEffective, but again, critical just means you're on or off. And then the last vocabulary word I have here is reactivity. Reactivity has units of dollars and cents. So back during the Manhattan Project, when they had to speak in code, they made up all kinds of funny units for things, and this just happened to be one of them. So you can have positive reactivity, and you can also have negative reactivity worth. And worth is just another way to say that I've given you some, a few dollars of reactivity worth, I've taken it away, and we might get into that a little later as well. So fundamentals in terms of the basic building blocks of a nuclear thermal rocket before I start getting into the finer details. So this obviously is the core with the yellow box around it. This rocket here is a museum piece, but this is within a textbook. It shows the major elements of this picture. So helium pressurization bottles here at the top help to pressurize the hydrogen propellant here, and then that gets pumped down. There's a regeneratively cooled nozzle, and then it gets pumped up through the reflector and then through the fuel. There's a turbo machinery here that you can't see in this particular picture, but a turbo machinery just like any other upper stage rocket engine. So think like the Centaur. The Centaur is like the workhorse of the Space Force. We're now on Centaur 5 in terms of the variant of Centaurs, but a lot of people like to take that same turbo machinery and just chop off the oxidizer part. You can use the same thing on here for turbo machinery. They're on the core itself, and I have lots more pictures that get into the details for this thing, but high-level overview, fuel in the middle, drums and reflector around the edge. The fuel is surrounded by tie tubes. So the fuel, you can't really see, at least I can on my screen, but there's a bunch of little holes in here where the propellant flows through, and then the tie tubes sit in the middle here, tie everything together. That's why they're called tie tubes. And then thrust, just like any other chemical rocket engine, is controlled by varying the mass flow rate of the propellant with the turbo machinery. And when you're actually looking to calculate your thrust or do your thrust estimates based on mass flow rate and velocity, exit velocity of your propellant, you can recycle the equations that you're used to using for chemical rocket propulsion. They're actually the same once you get to this nozzle part. So it doesn't matter that you had a reactor upstream of the nozzle. You can actually just use all the other equations you're used to using for chemical rocket propulsion at this point. So in terms of some very high level characteristics which set the nuclear thermal rocket apart from your ground reactors, in case there are any individuals out there listening to this that come from the terrestrial power world, you might be thinking, how is this different than those reactors? So for ground power reactors, they're obviously huge. Huge reactors. They operate for months to years. Whereas with nuclear thermal rocket engines, they're about the size of a large trash can. And they burn for minutes. And sometimes if you're going to Mars, you can have burn time on the order of hours. And then they, in order to turn them on, you turn them on quickly, just like a rocket engine. Rocket engines start up very fast, so on the order of, say, 10 seconds or so. Nuclear thermal rocket engines take a little bit more time to heat up. But you can ramp them from cold to hot in tens of seconds, so think like a minute or so. So in terms of the operating temperature of a power reactor versus a nuclear thermal rocket, and this is the thing that really sets it apart from the research in the power reactors on the ground, is this temperature. So I'm sorry I have two different units here, but 1,000 degrees Kelvin, Celsius, about 1,300 degrees Kelvin. And then over here you're talking 3,000 degrees Kelvin. So that is sort of night and day in terms of reactivity insertion. But this is much closer in terms of technology to the power reactor. In fact, this diagram shows a nuclear thermal rocket engine with two power cycles on it. So you can use a nuclear thermal rocket in a dual mode, power and propulsion. So hydrogen being sent through the nozzle, and then you close off that fluid cycle and use this closed cycle here to generate power. On the bottom here, some common coolants for the power reactors. We have water, helium, molten salt. Always hydrogen for the nuclear thermal rocket. That's our favorite, although you can put different propellants in it if you'd like. In materials, aluminum, steels, ceramics, but only materials that are able to withstand the very high operating temperatures are capable of withstanding the nuclear thermal rocket environment. So think graphite, tungsten, ceramics, etc. So this is a very, and again, a basic schematic of the nuclear thermal rocket, and very high level overview of the moving parts of the rocket. So the drums around the outside turn the reactor on and off. So they're lined with a layer of poison. Poison is a term in the nuclear community that just means an absorber, neutron absorber. And it stops neutrons from going into the U-235 to cause fission. The turbo machinery is another moving part that pumps the propellant in this particular diagram down to the nozzle, up through the reflector, and then out through the nozzle to generate thrust. So kind of pretty simple. And again, I want to emphasize, because when I teach aerospace propulsion, I get the question, even in the middle of a class, in the middle of a semester, where's the combustion happening? There's no combustion. It is the nuclear reactor is the thing generating the heat. The only thing that's moving or that's special about this, besides the fission, of course, is the drums and the turbo machinery. So I have here a video that gets into a little bit more pictorial detail into the NERVA rover control drums, and so it'll show you what those look like, and also you can see a little bit better what the tie tubes look like. They're going to pull one out, and you can kind of see that. So again, called a tie tube because it holds all the fuel together. You can see there's a plate here on the bottom that holds the fuel surrounding the tie rod. And by the way, if you go to YouTube, there are dozens of videos from NERVA rover on YouTube. So I encourage you to look. And also, I love this video because it just shows you can stick your hands into a reactor that's off. For DRACO, we're never turning a reactor on the ground, and people are always, people who don't come from the nuclear community are always asking, is it safe? Is it safe? And it's like, yeah, you can stick your hand right in it if you'd like. And here's a video that shows people doing exactly that. So there's the tie rod. You can see kind of the size relative to that person's hands. Sliding on the springs. There's a lot of vibration that goes on in the core. The springs help with compression to keep things from moving around. Of course, once you send things into space, you expect a lot of vibrations. And there's also flow-induced vibrations from the propellant going through the reactor. You can see the relative size of this core. This is the Phoebus reactor. This was the largest reactor from rover NERVA. So your typical nuclear thermal rocket engine is actually about the quarter of the size of this one. This was a gigawatt-sized reactor, which is the biggest, most powerful nuclear thermal rocket. And so you see the control drums on the outside, their relative size and placement of where those would go. And then kind of little zoom in action going on. And then the last part of this video just sort of shows it being rolled out into the desert to be tested in Nevada. Unfortunately, the Nevada test site, famous of course for detonating lots of nukes and making lots of craters, where they tested the NERVA rover engines, has been mothballed. It's been mothballed continuously since the end of the NERVA rover program in 1972. And so the engine test stand in Nevada is no longer available for us to use, even if we decided, instead of a space test, we're going to do a ground test. There's just nowhere for us to do a full power ground test of the DRACO reactor. This is where they used to do it. You see they're rolling it out on a nice little choo-choo on its way to the test stand. And off it goes. And I don't have a video of the engine being tested, although like I said, there's lots of these videos on YouTube if you're curious. All right, so getting to the actual startup. Like I want to make our nuclear reactor turn on and off. How do I do that? So you might start off by first looking at how do you do it typically for your power reactors. So for a power reactor, people are used to turning reactors on and off with rods. Rods work with gravity primarily, especially when you're working around people. You want to have something that's safe, fast, and fail-safe. If there's an accident, the drums will, or the rods will just drop from the ceiling and automatically turn the reactor off. For a nuclear space reactor, you're not relying on gravity. You are in zero gravity, so you have drums that turn, no rods dropping into the core. For shutdown, you pull the drums out, or you pull the rods out for the trust reactor, and then for shutdown on the nuclear space reactor side, you just turn the drums to turn it off. To throttle, again, you sort of put the rods in a little bit or pull them out a little bit to throttle the power. And on the nuclear space reactor side, you turn the drums by, a little bit, or maybe halfway in or out to throttle the power. And you also throttle mass flow rate, just like you would for a chemical propulsion system with the turbo machinery of the engine. Okay, so now getting into some more detail, so get you guys ready to go take classes in nuclear physics and engineering once you learn these things. So the next few slides are very important when it comes to how do you actually make fission happen. So nuclear fission is one big statistics problem. You're both trying to increase the population of neutrons in one concentrated area, and you're also trying to influence the energy distribution of those neutrons in order to increase your probability for fission. So the cross section is just a means to describe how well is this material going to actually take in a neutron or not. And obviously the thing that we want to be taking our neutrons is U-235. So we want our U-235 to have the highest cross-section for the neutrons. Other materials have cross-sections too. We don't want the neutrons to go to that. So for instance, for our particular reactor, which has Halu in it, tungsten, naturally occurring, has an enormous cross-section. And so for that reason, we would want to keep, tungsten out of the core because it would eat all of our neutrons. It's a great neutron absorber. So again, it's a statistics problem. The cross-section, macroscopic cross-section, is the sigma times n, which is nuclei per centimeters cube. Sigma, unit of barns, again, one of those funny Manhattan era vocabulary variable words. Barns means to hit the broadside of a barn. You want your cross-section to be so big that it's like hitting the broadside of a barn. So you increase your probability of capture of a neutron by having a higher cross-section, and again, it's a function of spatial. If you're all the way over there, you're likely not going to have a high probability of neutron capture, but if you're right in the middle of the core, you have a higher probability. So in order to increase the probability of capture of a neutron, you do what's known as thermalize the neutron. So you can either have thermal spectrum reactors, or which, as you can see here, nice high cross-section or fast reactors, which are not thermalized, so the neutrons are kind of going wild over here in the fast reactor. And again, hydrogen, so think like water, hydrides, make great moderators. So the lighter the atom, the better it is at moderating. So one way I like to describe the process of thermalizing a neutron and increasing the probability of capture of that neutron into a uranium atom for fission is to use a Gulf analogy. So you have to imagine uranium-235 like a hole, like in a Gulf field. And the neutron is the ball. And so if you are in a field which is 19.75 enriched with holes, it's roughly 20% holes. If you are in a Gulf field, which is weapons grade 90% holes, it's mostly holes, right? And so if you have a ball and you hit it as hard as you can, it's going to have a ton of energy, and it's going to go flying. So that's going to be a fast neutron. It's going to have a ton of energy, and there's probably going to be a high probability of capture only because you have a ton of uranium-235. But let's go back to the high-assay low-enriched uranium field, which is 20% enriched with holes, or even lower, let's say 5% holes. You have to hit that ball very gentle. You have to give it just a tiny amount of energy, very, very low energy, and that'll greatly increase your probability of capture of that hole, of the ball into the hole. Okay, so hopefully that's sunk in. So the lower the energy of the neutron or of the Gulf ball, the higher the probability that it'll be captured in the hole or in the uranium atom. We don't have that many holes in our field. We're only 19.75 enriched, so we have to thermalize our neutrons. We can't just have them all whipping around very fast. So how do we do that for the DRACO reactor in particular, because we're not using highly enriched uranium like they did in NRVA rover? We have to have moderator materials in our core. And so here are some examples, because again, the reactors are used to seeing terrestrially on the ground. Here are some examples. We have light water, gas-cooled, pressurized heavy water reactors. You have typically water is used as your moderator. That's a good way. You just dump a bunch of water into a reactor, slows down all your neutrons, or graphite. So for rover NRVA, even though they were highly enriched uranium, they could have gotten away with a fast spectrum reactor. They used a graphite-based core, and it moderated the neutrons. That was how they were able to get away with making teeny tiny reactors. Phoebus was kind of an outlier. It was one of their more massive reactors, but because they had graphite as a moderator, they were able to make an epithermal core for propulsion. Other moderators could be hydride-based or beryllium-based. So this is my last super in the weeds technical slide before everyone goes to sleepy land. So KEffective, this is probably one of the most important variables to a nuclear engineer. Everyone wants a KEffective to hover around 1. That's kind of your happy place for operating in a self-sustained fission mode for a power reactor. If a reactor or any other nuclear sort of device goes above 1, it goes supercritical, which is not a bad thing. It just means that it's increasing in power. If it dips below 1, it's subcritical, it's turning it off. And then this wheel here, these are all of the ways that you can control your neutrons, and all of these different variables go into controlling KEffective. So things like a resonance escape, thermal utilization, reproduction, fast fission, fast non-leakage. And so it's all about controlling neutrons, making sure they don't get away, making sure they're the perfect energy level at all times, and then you can sustain KEffective at 1. Okay, so now back to the fun history. All of this is fun, not just the history. So I have von Braun up here now. I had Kennedy earlier. Von Braun is another historical figure. Some say he is the father of modern rocketry. And a quote here saying the development of a nuclear stage not only provides major advancement in our space propulsion capability, but gives needed flexibility in our mission planning, and that the role of the nuclear rocket program is analogous to the comparison of the piston engine airplane in today's modern jet airliners. I've also heard, for instance, Mike Griffin, who is a previous NASA administrator, describe it as going from sailboats. I think he made the leap from sailboats to nuclear submarines or something like that. Maybe it was something in between. But it is definitely a big leap in propulsion capability for beyond what we have now. And so you see here, they were looking at using a nuclear thermal rocket, again, beyond the Apollo program, similar to kind of the uses that we could use it for today, such as going to the moon. This is a NASA picture. Or beyond to Mars. This is a 1970s concept. So in 1972, and this gets into the reason why the program was canceled, Nixon decided, instead of continuing the Apollo program, going from the moon to Mars, that we would focus on more near-term space shuttle and other ISS type of programs. So now we're kind of having a revival of the moon-Mars interest in the United States. So I have a few highlight fun facts about rover Nerva. It ran from about 1953 to 1972. It demonstrated that nuclear thermal rockets were possible when it comes to those performance metrics that everyone, it existed on paper back in the 40s and 50s. So we demonstrated 875 seconds specific impulse, 200,000 newtons of thrust, and thousands of different techniques and tests were run on these engines. So the nuclear thermal rocket engine as a technology got to flight readiness. It got to TRL 6. And here is a nice table here that shows all of the tests over time for rover Nerva. And it continues to be the best option for space flight. Like if you look around and see what do we have available to us that's better than chemical upper stage rocket engine propulsion, nuclear thermal rockets remain the answer. The physics just has not changed. And so luckily we have Bill Nelson here, current NASA administrator, showing his support for DRACO earlier this year in January 2023. Luckily we have a lot of support in DC and also nationwide going into this program and sort of recognizing that the utility that this rocket has for advanced space flight, just as they did. And then this is a picture of Kennedy visiting 1962 during rover Nerva. Okay, so now we get into DRACO. So this is, as promised, the second half of this lecture and the thing that maybe you came to hear about. But at least now you have some good background knowledge and you've been kind of given that 101 lecture about nuclear thermal rockets and how to make nuclear reactors work. So what will the Driggle program do? What are we going to do? Well, we're not going to do any full power ground tests. We don't have anywhere to do those tests. Those facilities have been mothballed, as I mentioned. And the rocket engine was already brought to a state of flight readiness. So why replicate that when we can just go straight to flight? We're going to use cryogenic liquid hydrogen. I think a lot of people may not appreciate the fact that The current on-orbit record for the utilization of cryogenic LH2 is about 12 hours with a Centaur upper stage, and so we're going to be up there for about 2 months, which is going to set a record. And so that will not be a light feat, but we're going to try to do it, and we're going to need to do it for our rocket engine. We're going to use high-assay low-enriched uranium fuel, which I mentioned. We're targeting a launch in February 2027 currently. And the focus of this program and what is going to constitute mission success is collecting data on the reactor using Halu. So this is the thing that's new again versus the NERVA rover program. So we're taking this on-orbit demo very seriously. We're not just going to launch it into space and then turn the ignition and fire it up immediately. We're going to run many different preliminary health checks, take little baby steps on our way to start up the reactor. Safety is always our #1 paramount focus. We want to make this not only a successful demo, but also one which gives everybody good feelings about how responsible we are with conducting a nuclear experiment. So not only is this going to be a first-of-a-kind complex system operating remotely in space, we're also going to have a first-of-a-kind fast-acting instrumentation and control system. So if you don't have instrumentation that you can rely on, then you can't rely on the fact that your reactor is healthy, and on top of that, that you could even control the reactor. So the first thing we're going to do is we're going to diagnose our diagnostics. We're going to make sure that we can trust our sensors, that we can trust our computers before we actually start to move on to control the engine itself with the computer. And then once we are satisfied that the sensors are giving us responses that we anticipated, then we'll start to move on to test the reactor and then the engine. And this is what I would call an ideal startup of a nuclear thermal rocket engine. If you look at the actual data from all the engine tests from NERVA rover, these lines were all over the place. The squiggles were up and down in the middle, not because anything was wrong, but just because they wanted to see what would happen. Like, what would happen if I dialed down this power over here and opened these valves over here? The reactivity would kind of shoot up and down and all over the place. Again, nothing would go wrong. They would just learn things about a fast-acting fission system and how it works as a rocket engine. So the startup of the DRACO engine, and this is the funnest thing for DARPA, and one of the biggest reasons why DARPA is involved, is the fact that since it does have Halu and it's going to be heavily moderated in the thermal spectrum, is going to have startup effects and reactivity feedback effects, which we anticipate are going to be much different than what we saw in NERVA rover. So this particular plot doesn't show much by way of feedback, and I have a slide later that does. It actually shows a very well-behaved startup. So you turn the drums. So here's the drum position going up. The chamber temperature starts to rise because once you turn the drums, you insert reactivity. So the chamber temperature rises. That's the fuel of the nuclear reactor. There's feedback, reactivity feedback from the hydrogen going into the core. That spins the turbo pump. There's a closed loop power that goes from the turbo pump to the core. And then everything starts to go up in terms of power, pump speed, chamber temperature, and then you level out here at your happy place. You notice here the drums stop moving way at the beginning. So it does a bit of its own power bootstrap, and it levels out to this place. That nuclear reactor. Every nuclear reactor has a power level that it's happy at, and then it'll stay there on its own. So I will step through these, and then I have a plot after this, which helps to illustrate exactly what's going on here, or why we are doing every single one of these particulate level tests. So we're going to start off with doing what we call dry zero power criticals. So that's a zero power critical test without hydrogen. And then we're going to move on to wet warm power criticals, and then wet criticals followed by tank-driven flow, and dry steady state runs. So insert a little bit of reactivity. What that means is that you turn just a little bit of the drums, insert just about 20 cents, and then we're going to stepwise increase 20, 40, 60, 80 cents, which, by the way, is a lot of reactivity. Even if you look at the device assembly facility in Nevada, they have a limit of how much reactivity you can insert, and it's around in this range. So we're going to get the reactor warm. Once the reactor starts to be warm, then we start getting feedback by way of thermal feedback. So once you, if you remember that wheel of things that go into KEffective, the actual temperature of the material affects the ability of a moderator in particular to control the energy spectrum of the neutrons. So what does that mean? It means reactor gets hot, power goes down. We obviously don't want that, but we can control it, and we will understand it better once we step through very meticulously these various steps. We're going to do one drum at a time, get the worth of every drum, and then we're going to start to leak hydrogen into the core. Hydrogen is a great moderator. It adds reactivity worth. It's going to start to increase the power. So just like in NERVA rover you saw in the previous, one of the previous slides, the drum stopped moving, but once you start to push the hydrogen propellant in, the power continued to go up. So we're going to see by how much for our core. And then we're going to start to actually drive the flow of the hydrogen, tank-driven flow, and attempt a rocket engine startup, which is obviously the thing that you want to see. So these are very good plots for illustrating all those words I said. The green slide is the reactivity. The green line. The blue line is the drum rotation. So you rotate the drum, you stop rotating it. But you see here the reactivity spikes and drops off. The power goes up over time. And you see this little yellow line in this particular example. You start to run the hydrogen. You get a little spike in reactivity again. And then you turn off the hydrogen early on and then rotate the drums and turn everything off. This is an example of one of the tests that we plan to do. This is a rapid 20 cent insertion right here. And again, 20 cents is just a little teeny weeny bit of reactivity. Hold for 10 seconds. And then we have 10 seconds of tank-driven flow. Let me just go back. For every one of these preliminary tests, we have done preliminary models and simulation to predict what they would look like. So once we get into space, we're going to do each one of these little tests. We're going to compare them to our models, make sure they match up, and then we're going to move on to the next test. For the code that DARPA is relying on, that same code was used on the kilopower crusty experiment. And so for that particular code, they did the exact same kind of experiment on the ground. For those of you who don't know, kilopower was NASA's power reactor program for space. It was very, very successful in terms of the experiment that was conducted. And so we have the same people as well, the same engineers working from the kilopower crusty program on the DRACO program, so extremely lucky to have them and their code. So again, the code was run on the crusty reactor for that program. They took the data, they matched it back to the code, made sure it was one for one, and then they moved on to the next step. So we're going to do that in space. In this particular plot over here, you see that we have 10 seconds of tank-driven flow at 2 times the pressure. You see much higher spike in reactivity. So you see here, a nuclear reactor is very complex. It's not just an on-off switch. There's a lot of neutrons sloshing around. You have to wait over time for things to settle out. You never know which thing is going to insert how much reactivity and by how much. So in this case, we have a big spike in reactivity for this much hydrogen inserted. Power goes up to this much, and then everything levels out. Not immediately. I mean, you turn the drums, and it takes a little while for the decay power to go down. You also have things like delayed neutrons that you have to contend with as well. So, and also, I want to point out this is a generic core. This is not the DRACO core. But this is one that's very, very, very similar to it. We obviously can't put the real thing that we're going to be doing in DRACO on these slides. So I get the question sometimes of why not use other propellants? I mean, why we could go to space with ammonia, methane, maybe even water, something that's storable and not cryogenic, an easy propellant. But for many in the community, in particular, not just from the NASA side, but in the rocket propulsion community in general for upper stage rocket engines, demonstrating everything that we can for cryogenic liquid hydrogen helps not only the nuclear rocket community, but also the broader community in general. So also, it'll also help the biprop community that uses cryogens or for cryogenic liquid hydrogen. If you did, for some reason, decide you wanted to go with another propellant, such as NH3CO2 H2O, you're going to get ISPs sort of on the order of what you can get with a chemical propulsion system with storables or cryogens, so it's not really that much of a performance increase anyway. So you always want to go with cryogenic liquid hydrogen. A few more things about cryogenic liquid hydrogen. You might be like, gee whiz, who cares? But again, it's a super duper hard problem for many, many different reasons. And not only do you have to keep it very, very cold, but it's going to be zero gravity, and it's going to be, I've heard it described as sloshing around in a washing machine. You don't want it sloshing around like a washing machine. You want it to be nicely settled in one part of your tank so that you can have propellant coming out of one hose. You don't want to be pulling out air or gas and pushing that through your reactor because you might have a disaster. So we are going to make sure everything is pressurized perfectly, control the temperature of the cryogenic liquid hydrogen, make sure it is staying cryogenic. And then, of course, we're going to need to measure how much cryogenic LH2 is in there as precisely as possible to know how much we have left to control the rocket engine. So just a few more slides here. And this is something that I think the public tends to be pretty interested in, and that is safety and how are we meeting current regulations and policies and things like that. So in the nuclear world, they have what are known as general design criteria for nuclear reactors. And so we, in accordance with standards, have set 4 GDCs of our own. Our prime directive is that we're never turning the reactor on the ground, and that makes our lives very, very easy from a safety perspective, because as you saw in the video earlier, people can just stick their hands in the reactor. If there's a launch accident, you don't have to worry about people picking up fragments off the ground. From a safety perspective, it's just like lead. As long as you do not eat the heavy metals, you'll be fine from a radiological perspective. The second general design criteria is we're going to prevent the reactor from turning itself on. And that sounds, it sounds crazy, like, but there's always the tiniest probability that anything could happen. And so we are going to put all kinds of neutron inhibits in there to prevent the reactor from actually turning itself on. In the very, very low probability case that somehow all the drums perfectly turn themselves, to create a perfectly symmetrical, that critical mass to generate fission. So we're going to prevent that from happening. The third GDC is we're going to prevent radiological risk to the public in accordance with NSPM-20. NSPM-20 is National Security Presidential Memorandum 20. That was a policy that was signed in August 2019. It actually made it easier to launch high-assay, low-enriched uranium space reactors versus highly enriched uranium reactors, because you used to have to go to the White House to launch all your nuclear space systems. But in the case of Halu, with NSPM 20, the sponsoring agency of the mission can, the lead of the sponsoring agency can do their own launch approval. So in our case, it's the Secretary of Defense that's going to be doing the approval for launch for this mission. But they have radiological risk criteria, both risk and probability. So we're going to be doing it in accordance with that, and that also helps us to get out of analysis paralysis with safety. So for the last GDC, we're going to dispose of this in orbit in accordance with Space Policy Directive 6 and other guidelines. So for instance, orbital debris mitigation standard practices is one the Space Force likes. Space Policy Directive 6 is another White House policy. So for being in compliance with that, SPD 6, it says that you need to put yourself in an orbit in which you are at the radioactivity level at which you were when you launched. And so for us, that's roughly 316 years. That's going to take us to get back to that level. And so every orbit, every altitude has an orbital decay lifetime. You will come back at some point. And the higher you go, the longer it takes for you to come back. So for us, 750 kilometers has an orbital decay lifetime of around 300 years. So we could go that low in order to comply with SPD 6. We will more likely be higher, so 1,000 kilometers or 2,000 kilometers. Those have an orbital decay lifetime on the order of thousands of years, tens of thousands of years. So we already have the United States has a nuclear reactor on orbit, SNAP-10A. That was our one and only nuclear reactor the United States ever launched. And that sits at 1,300 kilometers right now, and it's going to be up there for thousands and thousands of years. So we're likely going to be somewhere between SNAP-10A and 2,000 kilometers. So I like these pictures. I try to find these whenever I can, just people working in and around the reactor, just showing how safe it is. People just hanging out, having a picnic with the reactor. That's going to be us with DRACO. Okay, so looking ahead for the DRACO program, where are we now? Where will we be? So in about a year from now, we're going to be doing cold flow testing of the full-up engine without uranium in the core. And so this is going to be very important for validating things like mechanical structural tolerance of the core to flow-induced vibrations, and also that the turbo machinery works, the valves are working with the controller, and so on and so forth. We are procuring lawn lead hardware for this stage. So as you can imagine, we are going to need some specialized rad-tolerant electronics, and so some of that stuff is lawn lead. Phase 2 will end in about 2 years, and then we're going to go into phase 3, where we're actually going to start building the core with the uranium in it, integrate the engine with the rest of the stage in phase 3, and then launch early 2027 in Cape Canaveral via an SSL launch vehicle. So this is my closing slide here. There are all kinds of things you can do with a nuclear thermal rocket, because a lot of people like to ask us, well, what can you do with this thing? Well, I mean, you can think about it like a very fancy upper stage. Right now, what people do with upper stage rocket engines is they just, they deliver their payload to where it needs to go, and then they throw the upper stage away and they forget about it. So you can sort of reimagine, well, what if you didn't throw away your upper stage? You could actually fly it around in space and keep it parked in there, up there like a car. If you had some kind of refueling architecture for cryogenic LH2 in space, you can refuel the tank and continue to use it. And even for a nuclear thermal rocket engine, as I mentioned previously, even if you run out of propellant, you can still use it for power. You can still use it as a power reactor. You can take heavier payloads places faster, you can go farther, you can go, instead of from A to B in 2D Kepler space along what I like to call the lazy river, you can shoot up like an airplane. So think about it like the difference between cars and airplanes. So right now, we're kind of stuck driving from A to B with these chemical rockets along these roads. But with nuclear thermal rockets, you can go up and over like an airplane because you have that much more power available to move. So hopefully I didn't go too fast. I guess I might have been a little excited to talk to you guys, but at least I kept most people awake. So I will perhaps take questions. Thanks.
So we'll start with our resident physicist with the red microphone.
My name is Scott Matthews. I'm a member. I'm wondering if DRACO, if there's any plan on harnessing the energy from fissioning other isotopes, and in particular, if there's any sort of like a breeder reactor kind of configuration that would allow you to maybe take some of the fertile, say 238, and make it plutonium and get energy out of that as well, or is it just the U-235 that's going to provide energy?
Yes, it is just the U-235, and that's also one of the things that we are leveraging. We're trying to harness as much as we can from lessons learned from rover NERVA, such that we don't completely reinvent the wheel. We are already going with a different enrichment level of uranium with the high-assay low-enriched uranium. But I'll put that on my to-do list for the next one.
Blue microphone, our resident planetologist.
Kirby Runyon, Planetary Science Institute. I am a member. Apparently, the reflector reflects neutrons. Thank you. You're going to have a cryogen on orbit for 2 months. So, are you using the reactor to electrically power a pump to keep it cold for 2 months? And then, what is the orbital flight path for that DRACO would fly?
So we are looking at entirely passive cooling methods. Yes, it will be very impressive.
That would be. And then can you comment on the orbital flight path?
So we are hoping to do a series of inclination changes. We are currently in discussions with the performer about how much orbit raising we might do, but my hope and desire is that we insert into a circular orbit and stay there.
Okay, thank you.
Thank you for coming to provide your lecture tonight. My name is Edmund Fernandez. I'm a member. I had my question written down, so I'm just going to read it. The PSW's website's description of tonight's lecture notes a successful demonstration of a nuclear thermal rocket could significantly advance humanity's means for going faster and farther in space and pave the way for the future deployment for fission-based nuclear space technologies. As you may know, the U.S. Department of Energy and its National Nuclear Security Administration announced in December 2022 the achievement of fusion ignition at the Lawrence Livermore National Laboratory, a major scientific breakthrough decades in the making that will pave the way for not only advancements in national defense, the future of clean power, but also deep space exploration. So can you describe the potential opportunities and challenges of using nuclear fission thermal rockets versus nuclear fusion thermal rockets?
Well, I think I can answer from a personal perspective, because as you know, DARPA currently doesn't have a fusion propulsion program ongoing, but personally, I believe that DARPA will open up the door not only for the current fission program, so not only nuclear thermal propulsion, but also fission surface power, all the other unique space fission projects going on, but also for fusion. That's obviously going to be the next step in terms of power and propulsion. I think that there are many more questions than there are answers when it comes to fusion propulsion. But I would, hope that with programs such as this, that there are going to be a renewed sense of investment injected into that particular area, so that we can hopefully have a more accelerated development of fusion propulsion efforts, which I think might actually be easier than trying to generate fusion power, right?
Now, what are the plans for using nuclear rockets beyond Pluto?
Well, there currently are not plans to go beyond Pluto. I think right now people are just focused on the baby steps. First we get to the moon. We gotta do that first and then go to Mars. So focus is really on using the power and the lift capability of a nuclear thermal rocket to get those big pieces of cargo to those distant places first.
Yeah, I forgot to mention in my comment before that there are some fanciful proposals for using thermonuclear bombs for propulsion in space. I mean, they're not that big, not that heavy, and people thought they can put them in space and then they could explode them. And if you had the right shield, that the force from the explosion would accelerate your rocket. I don't know if people took that seriously.
Different kind of nuclear propulsion.
Different approach. All right, red microphone.
Hello, name is Matt McEntee. Not a member, enthusiastic admirer of this renewed space age. Maybe this is a silly question, but presumably in its path through the core, that hydrogen becomes activated, and what's the disposition of that plume afterwards?
So the hydrogen itself will not become activated, although, well, even in our case, we don't anticipate having any particles coming out along with the flow stream. But the core itself and the materials in the core are what are going to be activated, but not the hydrogen.
Bob Terry, I'm a member. A couple of questions. Could you briefly describe what the drums are and why rotating them is so exciting? But additional, because I don't know what the drums are in your machine. We've heard all this stuff about the drums, so could you tell me what they are and how they work?
Sure. So the drums are long cylinders made out of beryllium. Beryllium is, as the first question, or the second question I think asked, are made out of a reflector material. So if you turn them in one direction, you reflect the neutrons in, turn it on. If you turn the drums in the other direction, they have a thin layer of a neutron poison on them, so boron carbide, for instance.
Right.
That'll absorb the neutrons and turn it off. They, about a meter tall. They run the entire length of the core. There's typically 12, at least in NERVA rover configuration. You rotate them all at the same time. Okay.
So anyway, so this high assay uranium fuel is not laying around. You have to really work to get that. I just read recently that programs in Congress to enhance and strengthen our domestic fuel supplies of uranium, I guess of all grades and types, are kind of running at a standstill. Is this fuel supply bottleneck in principle a problem for this kind of propulsion in space? Or do we have enough laying around to last us for a long time?
So luckily for DRACO, our core is so small that we don't need that much Halu for the core. So the programs that have more of a problem with getting the Halu are the power reactors on the ground. Even the microreactor programs that they need like on the order of metric tons worth of Halu, whereas we need on the order of less than 100 kilograms, which is easy to get for us.
Thank you.
Sure.
My name is AJ Katari. I'm a member. Glad to be here, and thank you very much for fantastic talk. You mentioned, and I guess about using this for power also, this kind of an idea about power. What would it take to change this? Obviously, it'll have to be a closed loop solution. So can you sort of explain a little bit more about how we can change this from propulsion to power, let's say on Moon or Mars or Cis-Lunar space? Thank you.
So it's most easy to imagine a NERVA rover kind of configuration being used as dual mode. And if you look in the open source, you can see more details on how that's done. But typically what you do is you take whatever was the coolant loop for the propellant to cool all of the various constituent elements. So for instance, NERVA rover again, coolant would go in a tie tube, go down and up and out of the core, and then eventually back down through the fuel. For the power reactor, you would only have it go down and up through the tie tube, but not through the fuel. So it would go down and up through the tie tube and then back to a power generator, and then kind of a loop like that. So you would have some sort of inlet separate from the propellant inlet that would run to a separate tank of gas, whatever you're using for your closed cycle power generation. You would just turn that on, turn the propellant off.
Thank you very much. I'm wondering about, I don't understand this obviously, but as I see it, there's a propellant that you're using up that blasts out the back of the rocket, gets heated by the reactor. Can you just completely, like a gas station, refill this and use it for centuries on the moon?
Yes, and so this is something the Space Force is interested in particular, is on-orbit refueling. They have approached me quite a few times because it'd be a shame to put this in space, in particular for DRACO. It runs out of propellant, and the reactor will still be alive for decades. So if you refuel the tank, you can keep using it. It's exactly what is envisioned for a nuclear rocket, a long-term stage. So yeah, the answer is yes. You could use the port that you use to fill it up, just like you would in your car. Same port to fill it up to refuel once you get onto orbit. So I am certainly interested in that.
And it doesn't become more dangerous the more you use it, the reactor?
More dangerous. It is, so the electronics, so it's not shown in our artist depiction, are on the other side of the tank. And so you're going to do your on-orbit refueling with a robot or something. You're obviously not going to have like a person like sticking it in there.
No John Gurdon?
Yeah, so if the electronics are still on the other side of the tank, then they will continue to be on the opposite side of the radiation environment, so protected from it.
Question or two from the web. Blue microphone back there.
So the first two questions from Shravan Rao in Melbourne, Australia. Have other fuels ever been considered like thorium? And his second question is, what happens at the end of the mission?
Sorry, what was the second question?
What happens at the end of the mission?
Oh, okay. So we had a similar question to the first one earlier, and the answer was no. Just U-235 is being considered for this mission. And for the second question, what's going to happen to the platform after the mission? It's going to stay in space, similar, as I mentioned earlier, to the SNAP-10A. SNAP-10A was another on-orbit demonstration fission reactor. Once it was done with its mission, it was left up there. So we are going to do a similar thing, leave it in space.
Thank you. The next question is from Edward in Boston, who is a member. On hydrogen storage, could you talk more about the feasibility of ambient storage using metal organic frameworks?
Interesting question. So that you've finally a question that's outside of my area of expertise.
As you might imagine, he's a materials scientist.
Yeah, so I'm sorry I will not be able to provide an intelligent answer to that question.
Okay. Next question is from Frank Robert, also a member, also from Australia. And he asks whether there are science missions using nuclear thermal propulsion in early stages of planning.
Science missions. So too bad I couldn't drag my NASA counterparts on stage with me to take that question, although I know there's one in the audience. So science, that would be more of like a NASA question because they do the science missions. So perhaps not one for me to take here.
I think Alan Stern is probably interested in that. Microphone over here. Thank you for your letting us take those questions from the web. Appreciate it.
Hi, I'm Andrew. I am not a member. A question I had was looking ahead to potential manned missions in the future. Would there be need for like additional shielding or additional safety factors, and how much like mass could that potentially add?
So in terms of shielding, so we would take lessons learned from what the Navy does. So they have individuals working very closely with the nuclear reactors on submarines and ships. And there are proven shielding methods for working so closely to small reactors used for power propulsion that we would just adopt for in-space use. One thing that we like to say and remind people of is that space is extremely radioactive, so the space environment. And with a nuclear thermal rocket engine, you will actually expose astronauts to less radiation because you move them through space much faster. You get them in space and out of space faster. So they're not getting radiation from the engine. They're getting it all from space itself. You don't want people to stay in there very long. So hopefully that answers the good idea. Of
Red microphone.
Is that working? Yeah, my name's Joe Foreman, and I'm a member. And about 4 years ago, there was an accident in Russia that some say was a nuclear thermal rocket that killed most everybody around it. Do you know anything about that, or can anything be said that's unclassified about it?
I would rather not. I think if you Google it, the internet has plenty of information on it.
Yeah, but which of that information is believable? Just kidding. Okay, if there are no more questions, well, thank you very much. And thank you, Tabitha, for generously sharing your time with PSW and giving what I found to be a very, very interesting talk that is stimulating me to learn some nuclear physics. But before you go, we have some small tokens of thanks to you for giving the lecture and spending time with us at the reception and dinner and a little bit in the social hour here. The first is a signed copy of the PSW bulletin. For those of you who have trouble reading from the back of the room, it is interesting because it says why the society was founded and who founded it. It has a very nice statement about science and how science should be done. I think is worth reading in this day and age of politicized and message supposedly based on science. Sometimes it actually is. Also, we have a rosette for you, which we hope you will wear from time to time. That is the rosette of the society, and the stripes on the side are from the symbol for induction. One of the primary scientists who studied induction was Joseph Henry, who was the founder of the society, and for whom the unit of induction in English anyway is named the Henry. And finally, we have a signed copy of the announcement of your talk, which we hope you'll enjoy. And with that, thank you very much. And everybody, before you go, there are a few closing remarks. The next meeting, number 2481, will be on Friday, September 22nd, right here in the Powell Auditorium of the Cosmos Club. The speaker will be Yuichi Tsuda of JAXA, the Japan Aerospace Exploration Agency. Yuichi is the project manager and lead engineer on the very, very successful Hayabusa 2 project. He will discuss the engineering of the probe, the results of examining the samples it returned, and give us a glimpse of the future science returns from this still ongoing mission. I should say that Yuichi is coming all the way from Japan, partly just to give this talk, so I hope you'll all show up and have a good crowd for him. The 2482nd meeting will be on October 6th. The speaker will be Lori Locascio. She is the director of the National Institutes of Standards and Technology and Undersecretary of Commerce for Standards and Technology. And she'll be discussing infrastructure and research at NIST. 2483rd meeting will be on October 20th. The speaker will be Pri Narang, professor in the Department of Chemistry and Biochemistry at UCLA. She will be speaking on quantum communication and perhaps on certain aspects of quantum computing. 2484th meeting will be on November 3rd. And the speaker will be Ted Schultz. He's kind of local, and curator of Hymenoptera at the Smithsonian National Museum of Natural History. Hymenoptera comprise the ants, wasps, bees, and sawflies. Over 150,000 living species of Hymenoptera have been described, and 2,000 species that are extinct. So clearly they're not all going extinct now. A variety of these species are agriculturalists, and he will be speaking about the convergent evolution of agriculture and make the point that humans are not the only farmers. And the 2,485th meeting will be on November 17th. The speaker will be Bob Truog of Harvard. He will be speaking about defining death. He will be talking about some of the science considerations, medical considerations, considerations that have to do with people's belief in culture, and the law. So it's interesting because there are different legal definitions of death in the United States. And there is one interesting case, and probably just an example of many, in which a child was declared dead in California under the California definition of death. But her parents did not want her to be declared dead. So they moved her to New Jersey, which has a different definition of death. And in New Jersey, the dead child was miraculously declared alive. I think it'll be a very interesting subject for people because it illustrates the kind of complex mix of considerations that we face in a pluralistic, diverse, democratic society trying to grapple with these kinds of issues. It's also timely because one of the leading agencies that recommends how you define death just changed its definition. It changed the word, I think I'm going to get this backwards, see, I'm a little brain dead. It changed the word irreversible to permanent. So I recommend that you all come. Yeah. To all our donors, and a big thank you for sponsoring series and individual lectures, to all the people who pay their dues and maybe give us a little extra money. We have our great thanks. The sponsorships, the dues are crucial to the Society's financial well-being, and without them, the Society would have to substantially curtail its activities and have fewer lectures. This year we hope to have 20 lectures, which will be the most ever, except for Zoom, during the pandemic, because it's so much easier to do a Zoom lecture than in person. We actually did have 20 lectures in the fiscal year. And I'm hoping that the Society will be as fortunate this year as it was last year in sponsorship support, and that we will again be able not only to meet the dramatically increasing costs of operations, but also to expand what we do. If you are interested in being a sponsor or adding to your sponsorship, or you know someone who is, please come see me, or email or call. I'll be very happy to speak with you. Last but not least, please thank the people who came to this meeting and instead of just enjoying the lecture, have devoted their time and effort to doing the things that need to be done for us to reach the audiences we reach. So I'd like to thank Cameo and Erica Kane, Robin Taylor, Brad Calvin, Andrew Gunn. Bill Mitchell hasn't done anything yet, but he's going to edit the video. Let's see. And Colin, who ran the microphone. And I will now adjourn the do I have a motion to adjourn the 2,480th meeting? Okay, do we have a second? All in favor? Aye. Anyone opposed? I doubt it at this hour. So I now adjourn the meeting to the social hour. There are refreshments in the back of the room.